Hello, everyone. Thanks for joining us again today. My name's Charles Rice. I'm your host today. Today, we're going to be talking about practical considerations for component-based transfer path analysis. And your presenter today is Eric Sober. He's from the Business Development Automotive MBH Testing in Belgium. Eric, you want to say hello?
Sure. Good morning or good afternoon, everyone. I'll just briefly show my face here at the beginning of the session. So indeed, welcome also from my side. I'm a business developer here at Siemens, and I take a big focus on the topic of component-based TPA and virtual prototype assembly. Maybe a brief, just short introduction to what this session is about. I'll try to demystify perhaps some of the concepts that up to now have been mainly theoretically introduced to you, and try to show you some real case studies where we applied component-based TPA and show you exactly how we managed to get the best possible results for different applications. So I hope you enjoy the session, and I'll see you in a second.
Great. We're looking forward to it. Before we get started, though, just like to orient us within this series. So far, we've already talked about the importance of high-quality FRFs, and we started off this series talking about FRF acquisition techniques. We moved into a little bit of the theory behind what are block forces and frequency-based substructuring, how that allows us to assemble virtual prototypes for predicting the MVH performance. Today, as I said already, we're going to be focused kind of on the practical considerations for performing component-based transfer path analysis. But if this was your first time here, just to kind of give you a brief overview, system MVH prediction tool is VPA. Really break it down in the 4 steps: categorizing our sources. Second, storing and exchanging data in our component library. And once we have that information, we can make a virtual prototype assembly and start predicting the MVH performance. And that's what Eric's trying to help us to focus on today, is characterizing our sources with our actual testing methods and techniques. And I guess I'll turn it over to him now.
So this presentation is sectioned in 3 parts. So firstly, I'll give a very short recap on the theory part, just as a brief reminder, let's say, to make sure that you're up to speed. But the main topic that I want to go through is, first of all, a bit of discussion on methodology. So looking at some practical case studies, I'll explain exactly how we go about implementing CTPA for these case studies. And then on the practical case studies is actually looking into 2 different technical papers that we published on the topic. You can, of course, refer to these papers for, let's say, a full breakdown of that project. But what I've done is I've basically taken out the interesting parts to highlight in practice how we went about executing CTPA. For powertrain noise and road noise will be the 2 main topics. And I hope that the principles that we show here will be sufficiently clear how that can then be translated to also other kinds of components, because certainly this methodology is not limited to only E-powertrain or road noise. Let's just make sure that everyone is up to speed very briefly. If you remember from invariant loads, these are loads that are invariant because we mean that they are receiver invariant. So these are loads which are a property only of the source component that we want to characterize. And depending on the source components, you can look at 2 different kinds of loads. You have structure-borne loads that deal more with, let's say, the forces generated by the source. And the quantities that we want to quantify or measure here are blocked forces and free velocities. And then on the airborne side, this talks more, of course, about the sound radiation that components might have. The quantities that we use here are volume velocity or volume acceleration. And then equivalently, we can also talk about sound power. We want to obtain these quantities essentially for our components or for our source components. Now, looking is this overview of different methods that are available for obtaining these invariant loads. So for structure-borne, and you see this is divided depending on the coupling that you have to your receiver system. So for weakly coupled systems where the receiver is either very soft or very rigid compared to the source, we can either look at directly measuring blocked forces or directly measuring free velocities. And then in general cases where the receiver has, let's say, comparable impedance to the source components, the general purpose method, you could say, is called in situ TPA. The question that I want to answer today is, looking at all these different options that we have available, Perhaps at this point you might be thinking, okay, but which is then the recommended method to use, or what are the advantages or disadvantages of each of these methods in practice? And the answer to this question, as I think with many things in life, unfortunately, is that it depends. So depending on your application, you basically have to think about two questions, the answer to two questions that will help you to narrow down which of these estimation methods you want to use. So these questions are, first of all, and it goes in this order, where do you want to define the interface between your source and your receiver? So where do you want to essentially cut your source component from the rest of the assembly? And once you have decided where you want to create this interface, you should think about the kind of coupling that exists at this interface. And depending on the answer to these two questions, you can narrow down to one of these methods. This sounds simple in theory, I think, but I don't just want to leave you with a vague answer like it depends. So what we will do is we will look at some case studies now where we really go through this methodology, this workflow, and I'll show you that for different applications, there are actually multiple correct answers to how you can go about this source characterization. So for the next part, let's have a look at some examples of applying this methodology. And the first example, and these examples will also be shown in more practical detail in the case studies. So the first example is on E-powertrain. Imagine this situation that you are interested in characterizing this E-powertrain from the rest of the vehicle. You want to describe it as a component that you can use in some virtual prototype later on. Well, let's first consider how this powertrain is then mounted to the rest of the assembly, because of course, powertrains are typically not directly rigidly connected to the body of the vehicle. In general, there will be some soft mounting solution in between that has the objective of isolating as much as possible the vibrations from the powertrain to avoid any kind of negative response inside the vehicle cabin. So the first question, again, that we want to answer is where do we want to put the interface between the powertrain and the rest of the vehicle? And I think, personally, I think the most interesting spot to define this interface is by putting our cut line here between the powertrain and the active side of our mounts. So if we do that, if we put our interface here, it means that the structure-borne loads that we want to identify, in this case, blocked forces, are acting on the active side, basically, of our powertrain mounts. If we know that this is where we want to obtain these blocked forces, the next question that we need to think about is what kind of coupling exists at this location. And at this point, I will not make any assumptions yet. I will just say that for general applications, we shouldn't assume weak coupling exists. Weak coupling is kind of a special case where you really have very significant mismatch in the impedance of the receiver and the source. So in general cases, we should assume strong coupling, and that means that we want to apply this in situ TPA method. In situ TPA, schematically, it works as follows. We will not be able to directly measure our blocked forces at this point 2 of the assembly, but what we can do is we can directly measure some indicator responses, typically accelerometers, which are instrumented on the vehicle body. And then we want to measure the transfer functions from point 2, so the active side of our mounts, to these indicators. And as you see at the bottom, the blocked forces are then obtained by inverting that matrix of transfer functions and multiplying it with the indicator responses. In theory, this all looks good, but unfortunately, the reality is that this method probably will not yield ideal results. And the simple reason for it is that those mounts, which in operation are meant to isolate the vibrations coming from the powertrain to the body, of course, in this situation, they will also work to prevent the excitation energy from, let's say, that our shaker or hammer, whatever excitation source we use to measure these transfer functions, that excitation will, of course, also be dampened out before it reaches those indicators. In summary, for this method, there are some advantages and disadvantages that we can identify. And on the advantage side, what I do like about this strategy is that the interface is nicely separating our powertrain from the rest of the assembly. So these blocked forces at this interface points are very valuable because it means that later on, when we want to assemble this powertrain into some other vehicle assembly using, for example, different mount solution, or it could be that we have transfer functions on the vehicle that are generated by a CAE colleague, so it's not on some physical prototype. All of this kind of virtual design exploration will be possible using the same blocked forces that we identify here. So that is certainly something interesting, but again, in practice, in situ TPA in this situation will probably not work very well because these transfer functions will be quite noisy if we try to measure them over the mounts. Okay, so is there some other way that we could go about doing this measurement then? Well, one option would be to simply redefine the interface between the powertrain and the rest of the body. So using the same physical assembly, the same prototype for characterizing our EDU, we simply redefine the interface to being between the passive side of our mounts and the rest of the vehicle body. And again, we can use in situ TPA to estimate the blocked forces in this case. And the results will be something like this, where, as you can see, the source components has now changed from being just the EDU to a source component that is composed of the EDU and also the mounts. So the benefits of these methods is that, unlike in the previous case, the transfer functions are measured in strongly coupled conditions. So we don't have any kind of vibration isolation between the passive side of the mounts and the indicators on the body. So these transfer functions will be measured with high quality. That's certainly a positive. But the disadvantage of this strategy would then be that the mount influence will now be inseparable from the blocked forces that we mention or that we measure. With this strategy, the blocked forces are still valuable, but it will not be possible to, for example, investigate what would happen in a future assembly if we change our mount stiffness by some different mount solution. That would not be something that we can do. That doesn't always necessarily need to be an issue, of course. It depends on how final the design of those mounts are. So if you're not planning on changing them, maybe it's not such a big issue, but in general, it does take away a bit of flexibility. Okay, I already discussed two methods and they basically have the opposite disadvantage and advantage to each other. Is there some way to get the best of both worlds then? Also, that depends on the application, but in this case, very often it is possible to basically combine the advantages of these two previous methods. And the secret here is in the mounts themselves. So if we can assume that the mounts are isolating the EDU from the rest of the vehicle body, it means that if those mounts are sufficiently soft, then we can basically assume that the EDU is freely suspended, or we have an infinitely soft receiver. And this weak coupling condition is exactly what we need to do a direct measurement. So if the EDU is coupled to a soft receiver, we can simply measure the acceleration at the mounting location, so at the active side of our mounts, and we simply say that this is equal to the free velocity. Now, in terms of advantages, disadvantages, again, this is a characterization that is on the active side of those mounts. So it's the best possible separation of the EDU from the rest of the body. So again, we can investigate based on these free accelerations or free velocities, the effect of different mounting solutions later on. But it does require sufficiently soft mounts for this weak coupling assumption to be valid. In practice, and what I will show in the case study, is that for very heavy components like an electric drive unit, this tends to be okay. So for this specific application, powertrains in general, you might say, because of the softness of those mounts, this free acceleration method tends to give you the best of both worlds in a very usable frequency range. So far, we mainly talked about structure-borne loads. What about airborne loads, though? Well, the story is a bit simpler in this case because for airborne loads, we more or less always use the same methodology to obtain them. The strategy that we use here is called airborne source quantification, but in execution, it is very similar to in situ TPA that you have seen before. Essentially, what we want is we want to obtain these Qs or these volume accelerations at different phases of the EDU. So we're basically characterizing the EDU as a set of monopoles. And volume acceleration as a quantity is not possible to measure directly in general. So instead, we are going to use an indirect method to estimate the volume acceleration. And the way we do it is by measuring, again, indicator responses. These will be microphones in this case. And we also measure the transfer functions, in this case, acoustic transfer functions between these cue points and our indicators. And then again, it's matrix inversion that we apply. So that is what is giving us these cues. And as I said, this is in general the method that we always use for airborne loads. And the reason for it is that this method has quite a few advantages. So first of all, in terms of transferability, just like the blocked forces in the first and the third case, this kind of characterization is transferable to any other receiving body. So it's really on the level of the EDU itself, which is quite nice. But also important is that because we can basically always assume that there is weak coupling between the hard structural material of the EDU, which is probably made from steel or some other hard metal, and air, which in contrast is, of course, incredibly soft. So this weak coupling means that these cues can be reused to any other receiver as long as the EDU is in identical or similar boundary conditions. So no real disadvantages, I would say, to this method. Let's also briefly look at the methodology for road noise before we go into the practical case studies. For road noise, I could talk about some similar things as for the EDU, but I've chosen to look at some other potential use cases for how to characterize loads. The first one that I want to look at is basically doing a direct measurement. So if we want to characterize for a certain tire and wheel combo what the structure-borne loads might be at different vehicle speeds, if we want to make predictions on, let's say, road noise inside the vehicle cabin, this is certainly a quantity that we need to obtain. One common strategy to do this is actually to attach the wheel to a rigid test bench, as you see here. So these are test benches that I took, these pictures I took from Kistler. They work on this kind of test bench. And as you can see, the roller is able to apply some preloads to the tire, basically simulating, as you would have in reality, 1/4 of the vehicle weight that is acting statically in this case on the tire. And then we simply operate our tire at whatever vehicle speeds it is that we want to characterize. And using a load cell, these are wheel force transducers that are being used. We can essentially obtain the blocked forces through a direct measurement. And with wheel force transducers, you can even get that, including the rotational degrees of freedom. This is a very useful way to characterize our tires in the sense that the characterization at wheel center allows us to reuse those blocked forces later on for basically any suspension system or any vehicle body, test base or CAE base, where we would like to make a prediction on expected cabin noise due to road excitation. Additionally, and that's specific perhaps to road noise, is that we know that these rotational degrees of freedom are actually quite significant when it comes to the excitation generated by these tires. So for road noise, it's not really sufficient to just only take the translational parts. You cannot actually ignore these rotational components, and something like a wheel force transducer is quite convenient in also providing a way to measure rotational degrees of freedom at the same time. So this all sounds good, but yeah, there is one bottleneck to this method, and that will in practice actually be the frequency range where this can be applied. The frequency range where you can directly measure blocked forces is dependent on how stiff and how rigid you can make your test bench. And of course, as you go to higher frequencies, even the stiffest test bench made of steel or reinforced concrete will start to show some modal behavior, some flexibility at higher frequencies. And it's a bit hard to put numbers on this, but in practice, what we see is that most test benches are really only rigid up to, let's say, 1 to 200 hertz. And extremely stiff test benches, in the optimistic case, maybe allow you to go up to 400, but certainly not more. As I will show later in the case study for road noise, this is actually a limiting factor. So we do want to go higher than this frequency range allows. But yeah, this method will not allow you to do that, simply put. So the alternative will be to look at some other ways to obtain these invariant loads. And one way that we could do it is by forgetting about this test bench for a moment. And we're going to drive our tire wheel combo on the actual suspension system and vehicle. Any suspension system and vehicle could be used here, and simply apply in situ TPA for that. Now, for in situ TPA, and I'll talk more about this later, there is a complication here when it comes specifically to tire characterization, and that is that the physical connection between the tires, or the wheels actually, and the suspension system here on the wheel hub is quite complex in practice. So you have to assume that you have maybe 4 or 5 wheel bolts that are connecting these two components together. So if you look at the physical connections, that would mean that we need for every wheel bolts translational and rotational degrees of freedom. So that means 6 degrees of freedom per wheel bolts in a rather small physical surface area. So the density of this estimation is simply too high to expect any kind of stable estimation results from in situ TPA. So the reason for highlighting this case study is because it is one of the case studies where virtual point transformation plays an important role. And in practice, we see virtual point transformation popping up quite a lot in CTPA in general. Essentially, what we will do here is we will reduce our physical connections, again, those 4 to 5 bolts, to a single virtual point, which then also will have 6 degrees of freedom, typically at the wheel center. So schematically, the setup that we will implement, and I'll show it later in the case study, looks as follows. So from our physical connections, we're going to reduce to a single 6 degree of freedom virtual points. And then, of course, we are going to measure the indicator responses on the suspension system, then in this case, close to the wheel hub. I'll show some pictures of it also later. And we need the transfer functions from the virtual points to these indicator points. So that is, again, something that's using virtual point transformation we can obtain. And then finally, the blocked forces. So in 6 degrees of freedom, these will be calculated using the matrix inversion approach that we used before. Advantages, disadvantages. Again, it's a very useful way to define the interface between the wheels and the rest of the vehicle, because again, later on, these blocked forces can be applied to other suspension systems and bodies. Also here, we have both the translational and rotational degrees of freedom at wheel center. And again, those rotational degrees of freedom should not be ignored for road noise. And this VPT approach in practice will be much more simple and reliable compared to estimating blocked forces at the actual physical connections, the wheel bolts. The only thing that complicates things a bit is VPT. So VPT itself will also have some effect on the frequency range, and that needs to be validated. I'll show you later in the case study some sample results so you get an idea. But I can already say that basically for road noise, the structure board components doesn't really have to worry too much about the frequency range of VPT. Okay, final example that we'll look at from the methodology point of view is if you would like to still go to higher frequencies. Actually, I forgot to mention that on the previous part, but the whole reason that we go for these methods is to, of course, increase the frequency range compared to our rigid test bench. So the return on investment, you could say, is that using these methods, we can more or less easily cover the frequency range where structure-borne road excitation is relevant. So that is the benefit compared to the direct measurement methods. But let's say that you would like to go to even higher frequency ranges than what we can obtain using in situ TPA, because that's virtual point transformation does put some limits on the frequency range. Or let's say that you're not interested in redesigning your suspension system. It might be that you are a CAE engineer that is only responsible for designing the vehicle body. So you don't actually need to make any changes to the suspension or the mounts used by the suspension system. Well, one alternative setup that you could use in that case is a bit similar to what we did before with the EDU, is we simply increase the scale of our source components. So instead of defining the interface between the wheel and the wheel hub, we can also take the wheels and the suspension system together as a single component and simply cut that component from the rest of the body at the interfaces between the suspension system and the body. So this will make life easier in a way, because we can again apply in situ TPA here on the passive side of our mounts. So we can expect high quality blocked forces by estimating blocked forces at the passive side of the mounts. But of course, the drawback of this method will then be that the suspension system and mounts are now an inseparable part of those blocked forces. So this characterization is only useful for investigating different vehicle body designs, essentially later down the line. Again, it doesn't need to be a deal breaker, but it does depend on your application, who the intended user or audience is for those blocked forces. That is a quick rundown of the methodology that we use for defining or choosing a method for estimating blocked forces or airborne loads. What I want to do now is to go through two practical case studies, so showing a bit more of the actual setup that we used and showing some validation results to give you an idea on frequency ranges and accuracy that is possible when applying these methods. So the first case will be on this E-powertrain. And what we did in this case, again, these are based on technical papers. So this was a paper done with BMW. I'll provide a link to these papers at the end of the session together with some other resources. So you can always check if you want to investigate a bit in more detail than what I show in the slides. Simply put, in this paper, the objective was to do the following. We want to do a prediction of the expected cabin noise for a particular e-powertrain. And in order to get as accurate as possible of prediction results, what we did is we basically characterized this e-powertrain in terms of both the airborne loads and the structure-borne loads that it puts into the vehicle. Both types of load types were analyzed. And for the structure-borne parts, again, to make it as realistic as possible, we subdivided the receiver into individual components. So we have the EDU, of course, as a source component, but then we have the mounts that are connecting the EDU to the rear axle carrier. This axle carrier is then acting as some kind of passive component that is then further filtering the vibrations from the EDU before handing them to the trimmed mass body, the final receiver on the right. But of course, that axle carrier itself is also softly mounted to the trim mass body. The EDU, the mounts, the rear axle carrier, and the trim mass body were all characterized as separate components in this study. And we want to see how accurately we can then predict the cabin noise of this virtual assembly compared to the physical prototype, which is then also available. And the final bullet that I need to mention here is that in terms of the frequency range, because this is an electric powertrain, and for electrified vehicles in general, the frequency ranges tend to be a bit higher compared to traditional combustion-driven vehicles. So one of the objectives is not just the validation, but also looking at methods to get as high as possible of a frequency range in order to capture as many electrical phenomena as possible. All right, so let's start with the airborne loads characterization of this EDU. So as I explained before in the case studies, for airborne loads, it's a bit more simple than for structure-borne in general, because we basically always use airborne source quantification for airborne loads. What that means is that in our block diagram, we can more or less assume that the EDU is weakly coupled to the rest of the system. So we don't need to actually care about the rest of the system. We can measure these airborne loads either in the vehicle or on some test bench that delivers identical boundary conditions. So you would need to have the same mounting points for your EDU on the test bench in order not to have different boundary condition and changing the acoustic radiation. But what we basically did is we instrumented a acoustic exciter. So this is a Q sources QMHF, mid-high frequency source, I think it stands for. It basically looks like a garden hose that has an opening for acoustic excitation. And this is an exciter that can measure its own volume acceleration outputs. It can basically generate this kind of acoustical FRF, as you see an example here on the left, which is the Pascal per volume acceleration. So the indicator response per excitation generated by that exciter. These acoustic FRFs serve two purposes. The first is that we need local FRFs for our indicators for matrix inversion. So again, we estimate these Qs through matrix inversion using local indicator data and local transfer function data. And then at the same time that we perform these measurements at each monopole surrounding the EDU, we can also then directly measure the acoustic transfer function on the trimmed mass body. So we put a microphone inside the vehicle, and just at the same time, for convenience and let's say to reduce the measurement time, you can then also get the target transfer function. Again, this method works quite well. There's not really too many drawbacks to ASQ, which is why we tend to basically always use it. And one of the benefits here is that this QMHF works up to 10 kilohertz. So you can cover a very, very wide frequency range, including high frequency acoustic phenomena using this ASQ approach. Next, on structure-borne loads characterization. So this is a bit of a repeat, I think, of the methodology slides that I showed before. On the top here, this big red cross is drawn over basically the two in situ TPA methods that I showed earlier. As I explained, for applications like electric powertrains that are very softly mounted to the vehicle body, in situ TPA tends to always come with some drawback. Either you have very low quality transfer functions because you measure over your soft mounts, so your estimation accuracy will be very poor, or you need to redefine your interface and get blocked forces on the passive side of your EDU mounts, which will be of high quality, but again, it doesn't allow you to then have the flexibility to change to a different mounting solution in a future virtual assembly. So in this study, what you can see is actually a validation of this direct free velocities methods for an application like this one, where you can basically assume free suspension of the EDU to the rest of the vehicle body. And we did validate this. So we actually performed this measurement. So just basically taking triaxial accelerometers to the active side connection points of the EDU. And we measured those on two completely different receivers, once in black on the full vehicle that we used for the project, and then once on this EDU test bench, which obviously has very different receiver characteristics to the vehicle. But what you still see is that the free velocities are basically overlapping. So it's really showing that this method is delivering an invariant characterization of the loads generated by the EDU. Another nice benefit, except for the fact that the measurements are direct, so it's easier to perform a direct measurement compared to something like in situ TPA, where you also need to measure transfer functions and have some overdetermination of the indicators. A nice benefit here is that we were able to validate this up to 4 kilohertz. So that's quite a high frequency range, I would say, for component-based TPA. But for this kind of application, it still works at up to 4 kilohertz. The next
Eric,
components I need.
One question popped in.
Yep,
Is,
sure.
Why is the free velocity method not valid below 200 hertz?
So for free velocity, the assumption is a bit the opposite as for the rigid receiver. If you directly measure blocked forces, you want your receiver to be very rigid. If you directly measure free velocity, you want your receiver to be very soft. But I think you can imagine that even for the softest mounts, if you apply a very low frequency excitation to them, they will not remain soft down to very low frequencies. So there is a limit on, let's say, the distance over which a mount can be compressed. So for low frequency excitations where let's say the displacement of the excitation will be larger, you will see that the mount stiffness tends to increase. I don't exactly know for this project specifically why this was at 200 hertz. I might need to check the paper to see if they mention anything about it. But I would assume that this is the reason why we have this low frequency limit. It's simply because you cannot assume free suspension down to the lowest possible frequency. There will be some lower bound frequency where the free suspension assumption will start to be valid. Okay, thank you for the question also. So important is the mount stiffness. So the mounts that we use, again, we had to characterize them to basically be able to get a prediction up to the highest possible frequency range. And the reason that we needed to use some test setup, as you see here, so we have this rigid block on both the active on the bottom and the passive side on the top that we use to measure mount stiffness. Why are we doing that? Well, the reason for it is actually twofold. First, importantly, is that if you look at mount stiffness characteristics that are delivered by mount suppliers, you will see that also in BMW's case, the maximum frequency where they are specified is in this case only 500 hertz. The reason for that is that mount suppliers, I assume, are mostly using hydraulic test benches to measure the mount stiffness, and that is simply not a method that works up to sufficiently high frequency ranges. We need to be able to have higher frequency mount stiffness characteristics. Otherwise, the work that we did to obtain blocked forces up to 4 kilohertz will be more or less for nothing. The way that we do this, I don't really have the time, I think, to go into detail on this particular topic. You can always check the paper for the full explanation, but what it comes down to is that this test setup is allowing us to use, again, virtual point transformation to obtain the transfer function between the active and the passive sides of the mounts. And this method is called inverse substructuring because we then also remove the effects of these rigid blocks on the active and passive sides. So we really get the pure transfer function of the mounts in isolation. And because we're using VPT, one of the benefits is that the transformation itself is delivering both translational and rotational degrees of freedom. So unlike the mount stiffness that you will get from the supplier that is mainly focused on actual mount stiffness, you will actually be able to characterize the full 6 degree of freedom coupling between the active and the passive side of your mounts. So that is one very interesting benefit. The other benefits, as you see on the graph, is that the mount stiffness is estimated up to much higher frequencies compared to this hydraulic test bench methods. So again, this is a very important part of being able to increase that frequency range to something more useful for electric powertrains. A disadvantage of this method that I do have to mention at this point is that it is measured in free conditions. So this black bungee you see here is designed to freely suspend this whole test setup. And that does mean that we cannot apply any preloads on these mounts to obtain this mount stiffness characteristic. That's not ideal, obviously. In reality, we would like to have the mount stiffness characterized at the correct preloads. I'll show you in the next slide that it's not necessarily a deal breaker, but at the end of the presentation, I will also discuss briefly an alternative method that would actually allow to also take into account preloads for this mount stiffness measurement. But anyway, in the project, we didn't do any of this. We just used the mount stiffness characteristic without preloads. So for the final slides on this project, this is just the collection and calculation of our results. So what we have is we have implemented this block diagram as you see here. So the EDU characterized in terms of airborne and structure-borne loads. Mount stiffness characteristics for the mounts were applicable. I didn't show any pictures of this, but also the rear axle carrier and trimmed mass body were characterized in terms of transfer functions. So it's just a matter of collecting all this data and then using frequency-based substructuring, we can finally arrive at some prediction results for the virtual assembly of all of these components. And of course, we want to validate, like, okay, if we virtually assemble the vehicle, how realistic are the prediction results? Does that resemble the actual vehicle that we also have available? And as you can see, the match is actually quite good. So for some operating condition of the EDU, you see in black the measured cabin noise of the physical vehicle. And then in blue, we have the component-based TPA prediction results, which matches very closely. And in orange, classical TPA, which was basically used as the benchmark for decomposing the assembly. But also component-based TPA is based on a TPA model. So it means that these prediction results are very valuable for engineering purposes because we can decompose that blue line into the individual contributions, which are then coming from different paths. So here we have collected all of the different airborne phases or monopoles of the EDU into a single line, which is the blue one. And then for the structure borne, we can do something similar. And you can see how for different paths, different contributions to that total are obtained. So really telling us something on how to potentially redesign this EDU or mounting solution or rear axle carrier, or even on the level of the trimmed mass body, what exactly needs to be done to get those levels lower. Okay, I think that's perhaps enough on this cabin noise example. Let's spend the remaining time on the other case study, which is on road noise. Also, this case study is based on a paper. You can always check back for more details in that paper. The pictures which I will be showing of this case study are not from this Goodyear project. They are something that we have basically done as a research project separately, but I'm using those to show you the practical setup as we implemented it. This project has 3 main objectives, and that is a full road noise CTPA characterization, essentially. So first of all, we want to characterize invariant loads at the wheel center. So the structure-borne loads in rolling condition of the tires. And then we want to validate if those structure-borne loads can be used for predictions. And one time we will do this on a physical prototype of the vehicle, but much more interestingly will be afterwards, like with the BMW projects. We want to do this prediction on a completely virtual prototype. So without physically assembling any components, can we still get an accurate road noise prediction from these component descriptions? What you need to know about structure-borne road noise, because we are focusing on blocked forces here, so we're just talking about the structure-borne parts, is that it is quite complex in nature. So in terms of what is actually generating these excitations, rubber tires are super complicated components. There are many phenomena interacting on this tire as we excite it on the roads. We won't be able to describe that all in detail from our measurements, but what we can do is we can decompose road noise measurements to see the origin of that road noise in terms of frequency. So for some speed of the vehicle, I don't know at which speed this was measured, but what we can say in general is that structure-borne road noise tends to be limited to this 0 to 50 hertz frequency range. So this is the frequency range where for most vehicles, the road noise is dominated by the structure-borne parts. So afterwards, airborne and wind noise and other components starts to dominate over the structure-borne parts. So when it comes to blocked forces for road noise, this is really defining the frequency range that we want to cover. We want to be able to go at least up to 500 hertz. And if we can manage this frequency range, we know that the most important part of our road noise is captured. How can we obtain these blocked forces then? Again, I showed this picture earlier. Well, not exactly this picture, but this concept of directly measuring those blocked forces. This is an attempt that we made in our early days of understanding CTPA, basically a very rigid reinforced concrete block that we can attach the tires and wheels to, and we simply run it on our chassis dyno, and we measure the blocked forces with some load cell. This does work, but again, the frequency range that we can hope for will be on the order of, let's say, 200 hertz maybe, and we want to go up to 500. So we know that this strategy is not really the ideal solution. The recommended way to do this for road noise is actually using in situ TPA. So what that means is that we want to attach our wheels, tires to an actual vehicle and run that vehicle on the chassis dyno, and then we will estimate our blocked forces again using this matrix inversion methods. And this works up to much higher frequencies compared to the direct methods. Now for these projects, we also, just like for BMW, we want to validate that these blocked forces really are independent, so that they really are a characteristic of the wheel and tire. And the way that we do this is by repeating this in situ TPA exercise for 2 different receivers. Once we will do it on a tire test bench, and once we will do it on a vehicle. And if we get the same blocked forces, then it means that they must be receiver independent, of course. How do we, in practice, then execute this in situ TPA? Well, the first thing that we need are these indicator transfer functions, and these go from the connection interfaces to the indicators, which are then instrumented on the receiver side. When it comes to the connection interfaces, again, the physical connection is going to be our wheel bolts that are connecting the wheel to the wheel hub. These are the physical connections that from where the transfer functions will start. On the receiver side, what we have done here is we have instrumented a few triaxial accelerometers, which are then distributed on the knuckle and the upper and lower control arms, as close as possible, basically, to the actual wheel center. And what is important when it comes to in situ TPA is that you want to have some overdetermination here. So we are going to estimate blocked forces based on indicator measurements. You don't want to just have just enough indicators to do that estimation. You want to, as a rule of thumb, have at least a factor of 2 overdetermination. I'll come back on this point in the next slide. Finally, for the measurements, we're going to operate our vehicle on the chassis dyno at whatever operational speed it is that we want to get those blocked forces, and simply measure the indicator responses, and again multiply it with inverted transfer function matrix, and that gives you the blocked forces then. A very important concept here, of course, I already explained this before, but we have to think about this physical interface, because in this case, for this particular wheel, there are 4 wheel bolts, which means that in total, we would have 24 blocked forces to be estimated. Every wheel bolt has 6 degrees of freedom that need to be estimated. And then keeping in mind that for the indicator DOFs, we want to have at least a factor of 2 over determination. That would mean something on the order of 50 indicator degrees of freedom on the receiver sides. That's not really ideal. Firstly, because as I explained, it's probably impossible to get 24 independent vibration phenomena to be estimated on this small physical surface area. So numerical stability is going to be an issue. Secondly, it's impractical to measure 48 indicator DOFs on the receiver side. And even if we could, even if we had a big measurement system and a lot of accelerometers, it's still not clear how we would get these rotational degrees of freedom, because most measurements sensors, like triaxial accelerometers, they only measure the translational part. Of course, I already gave the answer before, but it is quite important to realize how important virtual point transformation is in the process of component-based TPA, because also here we will use that concept to simplify the connection interface from the wheel to the wheel hub to a single 6 degree of freedom points at the wheel center. And the simplification is quite huge, because instead of having 4 wheel bolts, I just have 1 virtual point, which means only 6 degrees of freedom to be estimated for the blocked forces and moments. And in terms of indicator measurements, that means that I only need at least 12, which is much easier to do. An additional benefit is that because VPT is a geometrical transformation, these rotational degrees of freedom will be automatically estimated as part of the transformation process. So it's not just simplifying the connection, but it's also delivering more valuable information, because I also get my rotational degrees of freedom here. How to set up the wheel for virtual point transformation? Here is one potential setup that you could use. So again, we need, these measurements are for the VPT itself. It's not for in situ TPA, so just keep that in mind. But we have 6 degrees of freedom to estimate in the virtual points. Also for VPT, because we're using a transformation here, we want to have sum over determination. So it means that in practice, we want to measure at least 12 plus degrees of freedom on the wheel sides in this case. So these 4 triaxial accelerometers that you see here, and then also for the excitations, I will come back on those later on. It's very important with VPT that you do validate your work as you go on, because there is a risk here with VPT that you apply some wrong calculation basically. But luckily TestLab will support you in this. So when you apply VPT in TestLab, there will be some indicators here that use some color coding to give some visual feedback on the quality of your instrumentation. And the things that we will check are, for example, the response counts, that is identifying if you have sufficient overdetermination to get a stable, numerically stable estimates of your virtual points. So in this case, we have 4 triaxial accelerometers. That's 12 degrees of freedom. So 12 is a factor of 2 more than 6. So that's okay. And then we have the condition number, again here only shown for the response points. So the condition number is a metric that we simply want to be as low as possible. It's a metric that says something about the invertibility of the geometry matrix that we use for transforming these measurement points to the virtual points. And in simple terms, it's telling you something about the distribution of your sensors. So you want to capture all 6 degrees of freedom of your virtual points. I think intuitively you can understand that if you put all your sensors in a very small cluster close together, that additional sensors are not adding additional information on the motion of that virtual point. So instead, you want to distribute your sensors, and this response condition number tells you something about the quality of your distribution. VPT is a geometric transformation. This geometric transformation means is that the input data is the coordinates and orientations of my sensors. So it's very important to have as high quality geometric information on the positioning of my sensors compared to the virtual points. As you can see in TestLab, this is an upcoming feature, I do have to say. So in the 2306 release of TestLab, we will allow you to load in CAD geometry of your test objects that you can use in defining the setup that you will be measuring eventually. So as you can see here, I can define my virtual points, my excitation and response points. And of course, I have full flexibility to modify the orientation and position of my sensors until the virtual setup on my CAD geometry matches with the physical setup that I have here on the left on the picture. This functionality has actually 3 main motivations why it is implemented. I think it's important to discuss on those. In terms of convenience, this means that when it comes to VPT, you can basically put your sensors wherever on the structure. So the software will handle extracting the orientation of your sensors. You don't need to manually align a sensor to a predefined coordinate system for this. The accuracy of the transformation will also be better because as humans, it's very difficult to align a sensor up to, let's say, a degree of accuracy. So we simply extract the coordinates instead. And in terms of reliability, that's CAD geometry that you see here and the virtual setup can also be used later on in the measurement. So it's not only for the setup itself, but it's also later on when I want to animate some results, or if I want to deliver, let's say, my virtual setup to a technician that needs to then execute the instrumentation. This all makes it much visual and easy to follow. Now, so far, I've only talked about the response points, so I need to briefly discuss on the excitations, because this is a bit more tricky actually. For the excitations, just like for the responses, we want to measure as many degrees of freedom per point as possible. And for the normal direction, so the green arrow here, that's quite easy, I would say. You can always just hit the structure with a hammer to excite this green direction. But the so-called in-plane directions, which are the blue and red direction here on these points, are much less straightforward. The solution so far has mainly been, and especially with impact testing, this is often done, is to glue a support block that you can use for the impact instead. So you don't directly excite on these red points, but you excite on the support block, and it's giving you the surface area that you need to excite in the blue and the red in-plane directions additionally. However, this really is not an ideal solution. The reason for that has mainly to do with what you see here on the graph on the right, and that is that you are applying an offset to your excitation. So instead of exciting directly the actual points, you are adding a certain parasitic moment excitation to the excitation that you are providing the in-plane direction. This is resulting basically in noise on the measurement that will not be measured, and your final quality or frequency range of the results will be lower as a result by doing this. For shaker testing, I also seen that this is a method that is often applied. So in order to be able to excite in this 3 degree of freedom system here on these excitation points, sometimes people are putting support blocks on their structure and exciting indirectly. But yeah, the same criticisms can be applied here for the shaker. Basically, if we want to maximize the accuracy of our virtual point transformation, a better approach would actually be to use an adapter. What you see here is the Q sources adapter that is meant for this purpose. So this is called the in-plane excitation adapter, which is a logical name for what it does. But basically, this adapter allows you to screw in a integral shaker also from Q sources, as you can see here. And you simply screw in your shaker into one of the predefined positions on the adapter. And the adapter allows you to consistently excite in normal and in-plane directions. Maybe I should just briefly mention, so there is a triaxial accelerometer in the center of this adapter. And the principle is that the excitation goes through the measurement axis or center point, let's say, of that triaxial accelerometer. So with this adapter, you don't have any parasitic moment excitation being applied to your structure. If we collect all our data, let's see what we can get out of this measurement data that we have obtained so far. So what can we do with all these measurements that we have done is, first of all, using virtual point transformation on the transfer functions that are measured around the wheel center. There are 2 important outputs that we get here. Firstly, one measurement will be performed with the source in isolation. So this is without connecting the wheel to the wheel hub. We can measure the impedance FRF matrix of just the source components. This will later on be used in frequency-based substructuring. And secondly, we want to connect our wheel to the wheel hub for the second part of the measurements, where we will then use VPT to measure the transfer functions from point 2 to our indicators. So the indicator FRF matrix is measured in coupled conditions. The next step of the process is that this indicator FRF matrix will then be inverted and multiplied with simply the indicator responses that we can measure on our chassis dyno. So we run the wheel at whatever speed that we're interested in characterizing. And through this simple multiplication, what we obtain is a set of blocked forces. And these are 6 degree of freedom blocked forces. So for particular speeds, the translational and rotational degrees of freedom at the wheel center. The last thing I need to mention at this point is these results look fine, but again, with VPT, it's very, very important that you validate the results that you get. So it's also something that we help you with in TestLab to do, is to validate the quality of your virtual point transformation and to assess basically the frequency range where this transformation can be applied. We have a number of quality indicators. I'll just focus on one of them, but it's perhaps the most important. It is called the rigidity metric. And rigidity is a metric a bit similar to like a coherence function in model analysis. So it's a value between 0 and 1. And rigidity is telling you something about the assumption that your structure is locally rigid. So without going to the whole detail of VPT, do just remember that VPT is a geometric transformation, and that means that it can only work if the structure between your virtual points and your measurement points, it has no flexibility in between. If that's the case, you can recalculate from the measurement points to the virtual points. So rigidity is a metric that shows you basically as a function of frequency how well that assumption is holding in practice. And as we can see for this particular setup, most of the points have a rigidity that is basically 1 up to the complete frequency range of 500 hertz that we need. But we can see that some of the points here start to drop off in terms of rigidity at already 250 hertz. So that's very useful information to have. But this rigidity metric is actually telling us after the measurements that there might be some issue with the setup. So the reasons for this low rigidity could first of all be that in reality, there is some flexibility in the structure. In general, it often occurs if you put your sensors too far away from the virtual points, you will start to get some flexibility in between. So reposition your sensors to be in as stiff and as close positions as possible to the virtual points. But what also reduces rigidity is inaccuracies in your sensor positioning. This is really where this CAD-centric instrumentation comes into play. But also for the excitation points, if you're using an impact hammer, for example, the actual alignment of your impact hammer with where you say that the excitation will be is not going to be perfect. There is always some tolerance on the angle of your hammer compared to the impact points. So this kind of inaccuracy tends to also reduce the rigidity function. And the end result is that this non-ideal setup will limit the frequency range that you can get in total. So basically, to maximize your frequency range, again, CAD-centric instrumentation and the in-plane excitation adapter are what help you to get more consistent results and higher frequency ranges. But going back to these projects, I just want to show that this whole process, which I have shown the pictures, we have also applied in this process. And what you see is that when we apply in situ TPA to either the test rig or the vehicle, you get very, very similar blocked forces as a result. So it's really showing that in situ TPA for road noise investigations is a method to obtain high quality invariant loads, describing the road excitation of the wheel. The only problem here is what is called the so-called rolling effect. So typical effects occurring between 90 and 100 hertz, where the motion of the wheel is actually changing somehow the dynamics and the blocked forces that you get in reality. So the deviation that you do see can be blamed on the so-called rolling effects. And the reason that we have this in the data is because the tire FRFs that we measured, for example, shown on this picture, these FRFs of course have to be measured in static conditions. You cannot have the wheel rolling as you are mounting these shakers and accelerometers on it. So we don't capture this rolling effects in this part of the measurements. The solution, and I maybe do have to refer to the paper for the full details, is that we have done some additional measurements on the rolling tires to still obtain the indicator transfer functions in rolling conditions. This involves putting your shakers on the knuckle sides of the wheel instead of on the rim. Again, full details in that paper. What I will skip to is that we were able to prove in this project that this kind of measurements allows you to obtain blocked forces that includes the rolling effect inside. So this description of the blocked forces is really the most accurate that you can get basically at the moment for this application. All right, so we've proved that we can get invariant blocked forces for road noise applications. The next step is that we want to see if those blocked forces can be used for predictions as well. Very shortly here, you can see a prediction results where in reds you have the measured driver microphone, so the physical prototype. And in blue, it is the predicted cabin noise starting from the blocked forces and then using transfer functions measured on the physical prototype. And as you can see, the comparison is quite close. So basically, we can use these blocked forces to make predictions on the vehicle side. But this example is not really so great yet because we needed still to have a physical prototype to do those transfer function measurements, which is, of course, what we want to avoid in context of virtual prototype assembly. Much more interesting, I think, is this last example where we will try to recreate our vehicle fully virtually and still see if we can get an accurate cabin noise prediction. How do we implement virtual prototype assembly in practice? Well, first we need to characterize our source components. So the blocked forces I showed on the pictures in the earlier slides, how we obtain those. In addition, what we need is the inertance or impedance FRF matrix of the tire themselves. So this is again an impedance matrix using VPT at the wheel center. Then the receiver side also needs to be characterized. You can basically choose here if you want to split the receiver into suspension system and body, or you can just measure it as like one monolithic receiver system that's composed of the two. That's, I think, what they did in this project. So it's just a single receiver containing all other receiving components. And we need here the impedance matrix of the receiver and also here the target transfer functions. So this is the transfer of the structure-borne loads to the cabin noise microphones. And then finally, we have the actual virtual prototype assembly step where we will then try to recreate this prototype fully mathematically. Again, this is using frequency-based substructuring and the virtual prototype assembly workbook in TestLab that allows you to create the virtual prototype. So here, every wheel is represented by these two blocks, and then the body is represented by a different block. In this case, it's a test-based body, but of course, these transfer functions could also be obtained through simulation instead. And then the validation of these results. So this is, I think, the most interesting results from this project. It is in red, the measured cabin noise for a particular driving speeds of the vehicle. And then in black, we have the predicted cabin noise using the workflow that I showed on the previous slide. So fully virtually assembling the vehicle, starting from blocked forces and all that impedance data, we can calculate the coupling of the wheel to the body and predict what the microphone response will be. And as you can see, the match is very, very close. So accurate predictions on virtual prototypes for road noise applications are absolutely possible. Perhaps the only annoying thing is that, as you see, again, between 90 and 100 Hertz, there is some discrepancy here. And so the question is if there is not still some residual rolling effects that is playing on these results. And actually, that is the case because in the measurements, we did take into account the rolling effects when it comes to the blocked forces. So rolling effect is eliminated from that part. But where we didn't take the rolling effect into account is on the tire inertance matrix measurements. So in the Goodyear project, we still did this using only static setup for the tire. Some rolling effects is still present actually, or not present, I should say, on this impedance matrix of the tire. We didn't know at that time in this project, but the good news is that meanwhile, we do have a strategy for eliminating this rolling effect in general using a very promising method that is called FBS decoupling. So this can be used in context of road noise, but as I mentioned earlier, I promised a different method for estimating mount stiffness in preloaded conditions. Basically, FBS decoupling is a way to characterize the transfer functions of any components in any boundary condition, including, let's say, for a mount preloads. So the basic principle of FBS decoupling is that we want to apply a preload to the system of interest. The direct measurements don't allow us to do this. So instead, what we will do is we will instrument our components on some receiver that allows to apply the boundary condition. So here it is rolling, the tire is rolling on the actual vehicle. Then separately, we need to measure the receiver that we used for the measurements. So either it's the vehicle or the test bench that was used for the components or whatever. We measure the environments that delivered the boundary condition, and we basically subtract it from the original measurements, to put it a bit simplistically. But the end result will be the components in isolation and also in the boundary conditions of interest. There is no time to go really into detail on that. I will link to the paper that discusses this in more detail. Just know that we have also applied this successfully on a suspension system example. So there is another paper that discusses this in more detail. Many different applications actually benefit from this kind of characterization. So for suspension systems, the issue is that you also want to characterize them actually under dynamic preload even. So you want your springs, you want to avoid this kind of stick-slip phenomenon when the springs are in some static condition. So you want them to be dynamically excited. And of course, all of this is completely incompatible with free suspended test setup. Of course, you are free to reach out to us for more information. If you have any questions, you can find our details here.